I'll do mine. Oh, wait.
Oh, yes. Can you hear me? Can you hear me? Yes. Can you hear me? Check. Yes. Good.
Oh, yeah, you too. Are you using Oh, you're using yeah. I might try this. I might try it out there and see if usually we're using errors.
Okay, welcome back, everybody. So I hope I gave you a sense of at least what the definition of underactuated was last time. If you got only one thing out of it, I hope that was it. And so, if your friends come up to you in the hall and say, "What does underactuated mean?" What do? You can give them the definition, right? And the control affine form, that was the easy form. That's fine. That's totally fine. Or you could just do a backflip, right? And then mic drop it and walk out of there. So but it comes up in all kinds of applications in robotics. You don't have to care about backflips to like it. I hope you will see applications of it if you care about vehicles, if you care about manipulation, if you care about certainly walking robots and flying robots. Okay, but today I want to start digging into the more of the technical content, although I consider this a background lecture. I think a lot of people, like I said, are coming from a computer science point of view, and my hope is that you will think more about dynamics in this class than you have in the past, and that you'll come to love dynamics and maybe even think about other forms of computation that you do through the lens of dynamics. So today I want to tell you a bit about sort of a classical, not even that classical, a view of nonlinear dynamics. It's actually, I try to channel Steve Strogatz. Steve Strogatz has a great book. Actually, I think I put a picture here. Nonlinear Dynamics and Chaos. There's actually, I just saw that there was a new version of the book that he published, I guess, a couple years ago. This is the older version that I've had on my shelf. And Steve has this incredibly graphical and intuitive way of describing what is occasionally incredibly complex and ideas in nonlinear dynamics. So I'm going to try to do some of that for you today and show you graphical analysis to build your intuition about nonlinear dynamics, and to give you some of the definitions that I hope, although there's some technical definitions, that they'll make a lot of sense because you'll see them graphically. So maybe the real goal is to have you love dynamics, but that's maybe not an algorithm for that. Okay, so I want to start with the simplest robot ever, which is just a pendulum. Okay, and we'll use that as our source of our dynamics to start with. So in general, I think you'll see that the notes and the course is organized with increasingly complex systems. And we're starting with the simplest, the pendulum. And we'll make the systems we care about, the robots we care about, more and more complicated. And we'll use the best tools we can to solve that particular problem, but as we make the robot more complicated, it's going to break our old tools, and we're going to have to go into a few richer tools or more proximate tools in order to go farther. But it's actually very valuable to start with a very simple pendulum, and we can understand it pretty well. So when I say simple, I said simple double pendulum last time. Simple means it's just a point mass, colloquially. And it's got a length L. We'll call this theta. Got some gravity. And the dynamics of this, we could read off just the way we did, we could derive them just the way we did last time. The kinetic energy of this system is just 1/2 ml squared theta dot squared. That's the velocity of this, L squared theta dot squared. And then the potential energy, kinetic energy, potential energy is just negative mgl cos theta. So if I write my Lagrangian and turn the crank, and I do my Lagrangian formulation, then the thing that comes out is just one equation, because there's only one variable this time. And it's one you might have seen before, ml theta dot, double dot, sorry, plus mgl sine theta. That comes from the potential terms. And that equals my generalized force or torque, which I've been calling Q so far. So that's what comes out of the Lagrangian. Now, there's a couple types of generalized forces or torques here that we want to think about. First of all, there's probably friction in the pin joint. So we'll put a term here. I'll say Q equals a torque that's proportional to the velocity, the damping. And then we'll allow that there's a torque actuator at the base, okay? You took all your research funding and spent it all on a nice Maxon motor for the base, and you can apply arbitrary torques without torque limits to start. Okay, so the whole thing comes out to be in the more sort of canonical form, ml squared theta double dot. A lot of times you'll see the B for second order oscillators like this on the other side, plus mgl sine theta equals U. Okay, so I want to start by trying to understand that equation and understand sort of in a deep and graphical way what that equation means. All right, so this is just a differential equation, right? It's a second order differential equation. This is the stuff of 1803 or your differential equations classes. So a standard question for a differential equation would be, if I give you the initial configuration, so let's say theta 0, and since it's a second order system, I also want to give you theta dot 0. Then the type of question you'd ask in differential equations is, where is theta as a function of time, right? That's the classical question. And I'm very sad to say that I can't solve that. I cannot write the solution to this for this system. It's like the simplest robot you'll ever touch ever, and this doesn't have a closed form solution, at least without going into at least with the elementary functions. So you can write the solution in some cases, if damping is 0, as elliptic integrals of the first kind. You put the damping back in, it gets harder. It turns out that integrating the nonlinear differential equations is actually really hard to do. Right? So everything you did in your DiffEq classes, that term didn't exist. It was a linear differential equation. The nonlinear differential equations, in general, we can't solve. Okay, so that's a little humbling. I just said this is the easiest robot we'll ever touch, and I actually can't even solve the differential equation. So what the heck am I supposed to do? Well, the point is that is actually the wrong question. You don't have to, you can understand a lot about the system. You can program the system beautifully without being able to solve that question, but you have to change your mindset a little bit from classical differential equations to thinking about what are my goals for the robot. So a better question, for instance, is what happens as time goes to infinity? Right? What's the long-term behavior of the system? That one, I guess you can probably guess. Right? If I've got a pendulum, it's got some friction, then I'd like to be able to show that it's going to eventually slow down and come to the rest at the bottom. Okay? And when I do control, maybe I can change that. That's a good question, and you can solve that question without having a closed-form solution to this, using the types of tools we're going to work on and work with in the class. There's other relevant questions you might ask. Maybe there's some really bad, someone put their lunch too close to the robot, and so you have to somehow prove that it is, it never enters a particular part of the range of theta. Right? Okay, that's really silly for a pendulum, but what if it's an autonomous car and you want to prove that it never drives off the road? Right? So does it ever enter a failure state? Which might be defined as some function of, I can even just write it as theta in this case. Right? That's a very meaningful question if you want to verify the system's safe. And you can answer that question without solving the differential equation, but you need a different set of tools and a slightly different way to think about it. And there's actually a lot of questions sort of in that, if you want to ask a performance question, saying like how fast does it get somewhere, oftentimes you can make statements actually without explicitly solving the differential equation. And that's a good thing because we can't. So the simplest tools to talk about, I think, and the most common tool that you'll have been exposed to start digging in these things is, of course, you can use linearization. So if I'm going to restrict my analysis to a small range of theta, it doesn't have to be around 0, it could be anywhere, then I could approximate this nonlinear sine theta with a linear function, and then I could do my differential equation type analysis. That works. Okay. But in these low-dimensional systems, then there's really this different tool that I think is underappreciated. And that's what Steve does really well, is graphical analysis. So let's play with some graphical analysis for the pendulum. Turns out, in order to plot everything, I'm going to make it even simpler first. So let's start by let me set u equal to 0 first. And I want it to be overdamped. And I want b to be large. Now, I actually think that the history, I told you a little bit about the history and talking to people who think about passive dynamic walkers and the like. It's been a really good experience for me to talk to people who think dynamics. There's a bunch of lessons that come in that you might not get unless you start talking to some hardcore scientists or dynamicists or whatever. What does it mean to make B large, right? First of all, what are the units of B in that equation? What's the units of damping? Yeah?
Torque over angular velocity.
Yes. So the units of that equation are torque, right? Every term in that equation has to have units of torque, Newton meters or kilogram meter squared per second squared, right? So ml squared theta double dot is kilograms meters squared per second squared, right? So B has units kilograms meters squared per second. Because it's being multiplied by theta dot, which is 1 over second, right? So when I say B is large, if I just say it in terms of this number, that actually doesn't really tell me anything about the behavior of that equation. What I really mean when I say B is large is what I want is that the B dot theta dot term works out to be much bigger than the ml squared theta double dot term. And I'd like to make this statement about that just in terms of B and ml squared. I don't want it to be a function of theta and theta dot. So this gets into this idea of dimensional analysis, which you come up with in the sciences, right? So in order to make some more sweeping statement about B that's relevant for the solutions of the pendulum, I'd like to somehow pick a characteristic unit, or in this case a characteristic time constant, to relate B to ml squared. So I'd like to somehow say B is greater than ml squared, but that doesn't compute, those aren't in the same units. I need something here that adds something in the units of 1 over second in order to make those have the same units, in order to have it be a fair comparison. Okay? So there is a characteristic time constant that's the natural, most of the solutions of the pendulum are going to follow, the natural frequency is the classical choice for the pendulum. If I multiply this by the natural frequency, then the idea is that this relationship should hold, for normal motions of the pendulum. So I actually want 1 over the natural frequency to make the units balance, so it's going to be square root of L over G. Okay? So there's this a little lesson in there, which I don't know if you get it from just seeing the one little example, but I find that dynamicists are extremely good at pulling simplicity out of complexity, right? So, if I was just thinking about the equations, I'd be stuck at the elliptic integral of the first kind up there. But somehow, dynamicists are kind of like, meh, put a characteristic time constant, you got the units the same, now you can make a statement, and that's going to allow me to simplify everything. This is if this relationship is true, that implies that this is true, that my terms in that equation, B theta dot, are dominate my terms that are due to acceleration. And that's going to allow me to think about a simpler form of the equations, which is a first order system. Yeah?
So when I saw this in the notes, I was a bit confused. I understand at a high level what's happening, but it feels hand wavy because we know what the natural frequency is because we've linearized these systems, so we know that. But for like an arbitrarily complex system, how do we know what to pick to make the units match to make this type of statement?
Yeah. No, there is an art to it. So the part that dimensional analysis tells you is you got to get the units right. But in the space of where do you pick that units, there has to be some sort of characteristic motion that you're trying to capture, right? If I was trying to capture something totally different, which is the response of this to super high frequency torques, then this might be a bad choice. So I don't have an offering for you that's like a general solution in all cases. But you'll see if in this sort of literature over and over again, dynamicists, being clever in picking out sort of these characteristic time constants, and or otherwise substituting in these variables. It turns out that actually this one's very relevant. I mean, even for a humanoid robot, there are characteristic time constants that are basically the natural frequency of the pendulum. So it might be with my center of mass relative to my center of pressure, but actually the governing dynamics of walking are basically a pendulum. And this one, you'll get some mileage even out of this simple one. Okay, so what I'd like to say is that ml squared theta double dot plus b theta dot is approximately equal to just b theta dot. I'm saying this term dominates. Okay? And that's going to give me a simpler equation than to think about, where all I really care about is b theta dot plus mgl sine theta. And if u is 0, it's just equals 0. Once we have a first order equation, then some new, then it becomes really easy to draw, basically. So just to write it out. Theta. Let me do one more simplification. So theta, to me, always implies that it wraps around in pi. And I know it's arbitrary, but if I change the symbol to x, I feel a little bit better about ignoring the fact that it wraps around in pi. So let me just write this as the x dot plus mgl sine x equals 0. So wrapping at 2 pi. Okay, so, or x dot equals mgl over b sine x. Okay, so if I want to understand the long-term behavior of that, then all I need to do is draw it, okay? If I do x versus x dot, colored chalk. Although it's a pretty sad box of colored chalk, we only have a couple colors today. They're all broken and small. Okay, so what does that look like? Negative sine x, so it looks like something like this, yeah? Where the height is mgl over b. Okay, so why did I bother plotting that? My claim is if once you've plotted the thing for a first order single variable equation, then this picture tells me everything I need to know about the long-term behavior. Even though I can't, even if I didn't integrate it over time, I can still answer a lot of the interesting questions. First of all, the first idea here is that this function crosses 0, at only a handful of points. Well, periodic points, but okay. So these are the fixed points of the system. If the system is at one of those points, it'll stay there forever. Right? It's a fixed point of the dynamics. But more so, I can just by visual inspection think about what happens away from the fixed points. When it's above, when x dot is positive, and it's restricted to this one-dimensional flow, then that means all the regions here where x dot is positive are going to be moving to the right. Right? Everywhere where x dot is negative, it's going to be moving to the left. And I can go through and mark that up throughout. Okay? And now I instantly observe that this fixed point is pretty different than this fixed point, right? This fixed point is stable. And we're going to be pretty careful before the lecture's over about what I mean by stable, because nonlinear system stability is a more delicate concept than in linear systems. Okay? But this clearly, trajectories, if I start my system at some place away from this fixed point, I have a tendency to converge to that fixed point. These have a different behavior. If I move even a little bit away, I'm going to go over to this fixed point. Okay? This is the case, this is the fixed point at the bottom. This is the fixed point at the top. Okay? Why is it so simple? What is this over-damped regime, this regime of making it first order? That's saying that my damping is so big that when I go a little bit here, it just goes really slowly down, right? And it doesn't even overshoot. That's the over-damped regime. Which, that comes up in lots of, that's like, in fluid dynamics, that'd be the low Reynolds number. It'd be you're moving through honey or something like this, right? This comes up in a lot of analyses. All right, and so this is the unstable fixed point. Okay, but I can even tell you more of the cool definitions about nonlinear systems. The region for which initial conditions converge to this fixed point has a name. That region here doesn't include that fixed point, so I'll use a dashed line. Doesn't include this one either, but it includes everything in between, right? I can color it all over, but it really is only points on the line, right? Okay, so this region here is called the basin of attraction. Of the fixed point, right? And the separations here are called the separatrix. You can imagine in high-dimensional systems, those are much harder to think about, the divisions between regions of attraction, but the concept still exists. I've got a region of attraction for one fixed point, a region of attraction for another fixed point. Somewhere in between them is the point where you go in one direction or the other, and there's a separatrix. Okay? So it's super easy to draw on this, but it's a concept that's going to give us a lot of power even in the more complicated systems. Sometimes these are also called regions of attraction. Okay, so the cool thing about this first order, this flow on a line, as Strogatz calls it, is that I could have done this analysis for any old system, right? It's not about pendulum. There's nothing about pendulum here. This recipe of look where the curve, plot the curve and look above and below the line, that works in general. So one of my other favorite examples is neural networks, right? So deep neural networks are hard to draw on the board. If I have, a million parameters and a million, my very, very complicated function, then it's going to be hard for me to draw it on the board. But I can draw a shallow neural network for you, right? So let's draw like the shallowest neural network example ever. And that's with one neuron, okay? But it's actually good. So do you know, I don't know if you know the story of the AUTAPs. I'll call it a shallow neural network here. Well, first off, so how many people have thought about recurrent neural networks? Okay, so because we're talking about dynamical systems, so a recurrent neural network, RNN, so a feed-forward neural network is just a function, y is some function of the inputs u. Okay, a recurrent neural network has a dynamics inside it, which in the continuous time is going to be some x dot equals f of x u, and then maybe y is some output. Okay, so the feed-forward case of a neuron might be that I have some inputs U going in here. Maybe I have some weights, weight 1, weight 2, weight 3 coming in. Maybe I have a sigmoidal nonlinearity here, or a ReLU or whatever. And I've got Y coming out the other side, okay? But a recurrent neural network is going to have some amount of connectivity from the output back to the input, right? So feed forward. And this doesn't make sense unless you say that there's some dynamics inside here. This would be, they'd call it an algebraic loop or something that, this model of sending your output back into your input only makes sense if you say there's something in here like a capacitor or something that takes time and tells me how the system evolves over time. So I'm going to get a neural network model. Okay. Now the simplest recurrent neural network model is something like this. Negative x plus that same nonlinearity, tanh of w times x. Okay, so that's a neuron with an input that's simply wrapped up on itself, a single input, and it's got a tanh nonlinearity. Tanh, we'll plot it a little bit in a second here, is just a sigmoidal function that goes between 1 and negative 1. Okay? But now I'm going to say there's some activation level of this neuron, I'll call it x, and the output of that, if you call it, tanh of this, gets fed back around into the input, so it's driving x dot up, but maybe there's some slow decay also that the neuron has a tendency, if this were to be 0, the neuron has a tendency to go down. Okay? This is the simplest model of a recurrent neural network, and it's called an AUTAPS. And the cool thing is, AUTAPSs are real, right? So you can actually, if you're an experimentalist, you can study an AUTAPS, okay? I did my PhD in a neuroscience lab, and I was the guy down the hall building robots, but everybody else in the lab was playing with neurons, right? So it turns out, I don't know if have anybody here ever record from a live neuron? No one today. Okay, but it's pretty cool, right? So you know what a neuron is. You can take it out of a slice of an animal's brain. Typically, the neuron's in pretty bad shape after you've sliced a piece of brain. You put it in a dish, you hit it with some chemicals to make it lose all its processes. So, all the connections, the axons and dendrites are in bad shape. You kind of have them die off, but then you nurture the cell back into health, and it makes connections to the other cells that landed in the small dish with it. And you get a small neural network in a dish, and then you can try to understand how that system works under a microscope. And the way you do that, for instance, is you actually you take a small pipette, you bring it down to the cell wall under a microscope of the neuron. You actually suck. I think maybe they probably built a machine by now, but like when I was in the year 2000, people actually went right, because they somehow decided that they could feel the amount of pressure you'd put on there better than they trusted a machine to do, right? And they'd suck the cell wall just a little bit into the end of the glass pipette. They'd stick an electrode down, rupturing the cell wall, but there was a seal, so it wouldn't actually go, like a balloon. It's that you could now stick an electrode inside, and you'd measure the potential across the cell wall, across the cell membrane, and that's roughly x. Okay, and now real neurons spike and do all these interesting things. So this x that we're thinking about here, this level of modeling, is a time average sort of frequency response of the neuron. So it's one level of detail away. It's not talking about the individual ion channels going psh, 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 psh. It's sort of how often is it firing right now. But these models do roughly, I mean, you need more coefficients in front of them. These do roughly capture sort of some of the behaviors you see in a neural network. So the cool thing is you can actually take a cell out, separate it from all its friends, and have it grow by itself in a dish, okay? So there's just now one neuron in a dish. And what is that poor neuron doing? It's reaching its dendrites out as it grows healthy again, its axons out and its dendrites out, and it's making connections to anything it can, which just happens to be itself, okay? And the pictures, look like this, right? So that's a cell in a dish reaching its processes out and connecting to itself. Okay, so why would you ever want to study that? Well, first of all, there's less things to record. It turns out once you've stuck a big electrode down in there or whatever, and you want to stick another one in, you need to suck twice, and you need to be pretty good at it because the neurons don't last forever, and so there's this. It's actually great because you put the electrode in, and the way they give themselves feedback is they'll actually hook it up to a speaker. So once the neuron starts firing, you hear on a speaker in there, and you hear the healthy neurons going, chittering away or whatever. And then there's a sad moment where it goes, and then never chirps again, right? So, and depending on how well they did that initial sucking, it'll last, 10 minutes or 4 hours or whatever. The best people would do it for hours at the time. So you got to do, you're trying to do multiple neurons all at the same time, and it's hard. And so people would do pairs of neurons, and those were groundbreaking experiments. But man, way better to just have one neuron. Okay, one thing to measure. You'd kind of know what's going on. And the interesting thing was the conversation that this AUTAPS might actually be sort of the most basic element of short-term memory. Right? So, and we're going to try to understand that with graphical analysis. So why does that equation, this x dot equals negative x plus tangent of wx, why could that be a model of memory? Right? Well, there's a great paper about it. But there's another thing that you might have heard of. How many people have heard of LSTM? In recurrent networks, okay? So LSTM is basically this, and I pulled it up. It's got the same tangent, it's got an X floating around, it's got a bunch more stuff. When you look at the equations for LSTM, do you know the Swedish chef from the Muppets? He's kind of just throwing all kinds of ingredients in, and I feel like this was just somebody was kind of throwing nonlinearities in. Hey, we want to make it do this. Hey, we want to make it forget. And so there's a mess of equations there. But we'll do like the simplest possible version of the LSTM here, and I hope I can give you the pictures for it. So the claim is this is a reasonable model of short-term memory. Let's work out that claim with pictures. Actually, I'll leave that here so that I'll draw it over here. So all we have to do is plot x versus x dot, okay? And we should be able to get the basic gist of it. So first of all, you know what tangent looks like. I want to make sure you know. So first of all, if I have x, then if I have a line here that has slope w, so this is the slope wx, then tangent is actually pretty cool. It has at 0, it has a slope w. The gradient of tangent is w, and then it goes away like this. Okay, to 1 and negative 1. This is tangent of wx. Okay? And then what does negative x look like? Because I'm going to combine those two. I'm just trying to plot that function for us here. So this is the function negative x. And then if I add this tangent on top of it, then I get a curve that's sort of, let me add 1 to this and subtract 1 from this, and I get a curve that does something like this. Multicolor. Okay? Now, if w was exactly equal to 1, then it would look a little different. Oop, multicolor. It would come in and just kiss this and then go down, okay? But if W is greater than 1, then I get, those are going to be on top of each other, right? Despite my artistic limitations. So this is the W greater than 1 case. This is the W equals 1 case. All right, so let's look at the W greater than 1 case. Where are the fixed points? 3 fixed points. Which ones are stable? Oops, did that wrong, didn't I? So these two are stable. Okay, and this is an unstable fixed point. So why is that possibly memory? Well, I have to do a little bit more, but first of all, it's sure interesting to sort of think that for a lot of different initial conditions, I kind of lock in to only a few possible states, 2 possible states. This one's close to 1. This one's a little close to -1. You could think of this kind of like a latch, right? A memory element. It snaps in. Maybe to make that more clear, what if I had an extra input to the neural network? What if I did x dot equals -x plus tanh wx plus u? So let's say I'm going to send in an extra input. What's that going to do to my curve? If I plotted wx plus u, then adding u is going to allow me to shift that tanh around, left and right. Okay, so if I apply a positive u, this curve shifts to the left, which is equivalent to this thing shifting up. Okay, or if I do negative u, it shifts down. So let's say I'm hanging out around 0, even though it's unstable and it won't stay there. And if there's any noise, it'll pick one of those 2. And let's say I just sent in, u is normally 0, let's say. U of t. I'm puttering along at 0. What if I just turn it on for a little while and then turn it off? Okay? Then what's going to happen? It's a little bit of beauty. I'm now going into another dimension, and I've only drawn 2 of them. But you can imagine that when it's here, the dynamics are governed by this equation exactly. I'm there. It's going to go to one of these 2 fixed points. If I now, for a little bit, by putting in an activation, shift this thing up, this fixed point will actually disappear. This fixed point actually doesn't even move that much. Suddenly, all these states move towards this fixed point. And I turn it off, I shift it back down, and it's latched. Right? So in this sense, this system gives me memory. Yeah? Now, is that clear? Yeah? And if I wanted to go the other way, I could send a negative u, right, and it'll kind of latch it in. If you know the LSTM literature, I didn't, I guess, write it down for the people that didn't raise their hand. LSTM is long. It's a recurrent neural network. It's the type of neuron you'd put in your artificial neural network. It's long, short-term memory. And the idea is that neural networks have sort of 2 types of memory. They have long-term memory, which is the weights. There's learning that happens over a very slow time scale. There's short-term memory, which is its current activation, x. And they want something in between, which is like a long-term persistence in x. And they get it with these kind of latching mechanisms. And they say that helps, wherever I put the slide, but that helps, longer temporal horizons in reinforcement learning and neural networks. There's another concept that comes up in the LSTM literature is they have gates, extra gates for remembering and for forgetting and things like this. So what does a forgetting gate look like? Let's just do the forgetting gate. So people have found just experimentally, I guess, that if they put in an extra input to the network, which is like, you will forget now, then you can understand that in terms of this graphical analysis, right? So the forget gates, again, it looks like Swedish Chef, but roughly the forget gate, I'll write it over here, is something that turns off this negative x. Okay, so you can look at it as like f minus 1 x plus tanh, where you think of f as being either 0 or 1. In practice, it's implemented with another sigmoid, but basically, if f is 0, then you've got the original equation I have here. If f goes to 1, what does it do? It turns my whole differential equation, my whole dynamical system, into just the tanh. I've lost my fixed points at 1 and negative 1, and I'm going to go back towards 0. Right, so this thing could just, you put a little stimulation in, put it there in the equation, and it'll make the system forget. And then you turn off, f goes back to 0, and you're back to your original system. Okay, and you can see it all on a picture. Okay? There's like so much more you can do with these pictures. I just want to give you the one more concept here, which is that people study the way those, we already saw it. As I started putting u in, I could move this equation around. I could move this curve around. And as I do that, the location of the fixed points actually move. If I move it enough, if I add change u enough, or change some of my parameters, change w enough, then fixed points can actually be created and destroyed, which is a nonlinear thing to do. Linear systems don't do that. Nonlinear systems do. You can have fixed points that just poof, disappear, fixed points that appear out of nowhere, seemingly. Okay, and so there's an important idea in nonlinear dynamics, which is what do the fixed points do as a function of the parameters or the inputs? And it's called bifurcation analysis. And the bifurcation is that moment where you have some splitting, or creation or destruction of the fixed points. And the way it plays out here, if I just take my original version of the equations here, negative x plus tanh wx, that was the simplest form. I would make a plot. Let's take the parameter w, and what I could do is say as a function of w, I'm going to plot the location of my fixed points. So remember, the slope of that line is w right at the origin. So when w is small, or even w being negative, it turns out I have, like this blue curve, I have only one fixed point, and it's at 0. You with me on that? If w is small or even negative, I have a single fixed point. It's like the blue line. That blue line is roughly what happens when w equals 1. So when I'm over here, my fixed points, I have only one of them. It's stable. I have one of them, okay? And that happens until W equals 1. W equals 1 is the bifurcation point, because that's when the slope of that hits 0. If I go greater than 1, I cross the line, and I have now the 3 fixed points. I continue to have a fixed point at 0, but suddenly that fixed point becomes unstable, and typically in a bifurcation plot you would now do that as a dashed line to say that's an unstable fixed point. But I also have these new ones. They start close to 0 and then move to 1 and negative 1. And the plot, which is in the notes more carefully, it looks like this. As a function of W, my sometimes I will use X star to note a fixed point. So that is affectionately, that's the other thing about dynamicists. Not only are they just fun people and they are good at dimensional analysis and simplify things, they also come up with goofy names for everything. So this is called a pitchfork bifurcation. Go figure. And you can, if you go through Strogatz's book, you'll realize that there's a bunch of ridiculous names for bifurcations because there's lots of geometries that happen as you create and destroy fixed points. And so there's the blue sky bifurcation, and there's the, I named it after myself or my kid bifurcation, and there's all kinds of stuff. So if you want to name something important, you could find a star or find a new bifurcation and put your name on it. It's good business. Okay, so I don't the bifurcation analysis is not going to scale to humanoid robots. But the concepts, the point that I want to get across here is that nonlinear systems are a different beast than linear systems. The very idea that I can have multiple fixed points is already unique. The fact that if I change my parameters or my inputs or whatever, I can move those fixed points, that's totally different. And it's kind of the point. You'd like to build controllers, for instance, that move these fixed points so that the system does its thing and ends up where you want it to end up, right? So you'd like to somehow control the location of those fixed points. And maybe that's the right way to think about it, is that I'm just going to set the steady state and let the system drive itself to there. Okay. What would I think are we asking about the pendulum in the problem set? The pendulum bifurcation? I think that's still in there, right? Yep. So we'll have you do your own pendulum, the plot for the pendulum bifurcation. But how does the pendulum, if I were to take the pendulum and now apply a constant torque, you can sort of think about that really quickly. What if I made U be a constant, or even let's just call it C to make it clear that it's a constant here. We had my original curve, which of course has a fixed point here and a fixed point here. What happens if I add a little bit of torque to it? Where do the fixed points go? If I start applying a little bit of torque here, it'll fight gravity a little bit, and the fixed point moves here, right? And you can see that if I hadn't erased all the sine waves. Yeah, if I added U in here, that's going to shift this whole curve up or down. Okay? So if I shift this up, this fixed point's going to move to the side here. This one's going to move this way, right? Do you get that? So that's the upward fixed point, which is actually going to go the same direction. It's going to, if I apply a little bit of torque, my fixed point's moving to here, where that's exactly resisting gravity. And now, if I dictate it a little bit this way, it'll go, right? If I dictate it a little bit this way, it'll go like this. A number of years ago, when I was a young faculty, I used to bring a pendulum and with a big Maxon motor to the class, and I would put this here, say I would say, watch this. This is how the bifurcations move, and I would show those fixed points. And then I would actually, I remember the fateful day when I said, what happens if you push U above here? And all the fixed points go away, right? And I said, then it would go unstable, right? And there were velocity limits that were supposed to be in the code. I don't know what happened to those that day, but and there was also like hard limits on the actuator. Long story short, I threw the pendulum across the room. I think they remembered the lecture, but I now bring simulation to the lab. Right? All right, so but just to make sure, and this is more to show you that you can play with it afterwards. But if you want to develop your intuition, then if I start applying a little bit of torque, this is the underdamped pendulum, right? So it's wiggling around that fixed point. It doesn't have as much damping, but it goes to this sort of new fixed point, right? And there's a critical point where you've added enough torque so that it's MGL, it matches the MGL, and you go up and around, and you throw your pendulum around the room. Whoa, and off it went. Okay. Any questions on that stuff? All right, so let's call that good on first order one variable dynamics and go to 2 dimensions. Okay, so we want to understand the original pendulum equations now, which have that theta dot in there. So I'll get us away from this overdamped regime and see if we can still do some of the same graphical analysis. So I've lost people here before. So if you haven't done phase portraits before, pay attention. So now I suddenly have the system I'd like to plot has 2 variables of interest, theta and theta dot, and the dynamics are x dot equals f of x, which is like plotting theta dot, theta double dot. Right, so this is a vector equation now. I was plotting a scalar function before, now I'm plotting a function with 2 variables in, 2 variables out. How do you plot 2 variables in, 2 variables out on the board? If I had 2 variables in and 1 variable out, I'd make a surface over the, a mesh or something. But this is 2 variables out. So the way to plot that is theta dot, and for every theta and theta dot, which if I could draw a surface coming out this way if it was just 1, but for 2 I'm actually going to draw a vector at every point. So for theta dot at this point, I get a vector which has direction theta dot, theta double dot. So it's a vector field, and I can draw this all over the board. And for every point of the function, I can draw a vector. Yeah? So let's draw the vector field of the pendulum. So the first thing is it's easy when theta dot is 0, which is along this axis here. Theta dot is 0. That's an easy thing to plot. It just looks like theta double dot is g over L sine theta, negative g over L sine theta, which is, so the theta dot term will be 0, if you think about it. So every vector along this line is going to have no horizontal component. Theta dot equals 0 implies that the x component of my vector, which was theta dot, is also going to be 0. The y component is going to be theta double dot, which is just g over L sine theta minus. Okay, so for u equals 0, that this is, it's going to look like a vector field that has my sine wave again. Okay, and this is the pi. That work? Yeah.
Are we still assuming that the damping term is dominating the acceleration?
No, good. So I'm allowing the damping term to come back in. So b does not have to be 0. In fact, let me draw it first because I'm about to have to make that choice. Let me say that b equals 0 in this case. So it's not explicitly not the large damping regime.
Sorry, okay. But not the large damping regime nor the zero damping regime.
I'm going to draw the 0 damping regime first, but we will generalize it. Good question, thank you. So if I were to plot now along the theta equals 0 plot, if theta equals 0, I get sine is 0, right? So that term doesn't contribute anything. And I ended up getting along this just horizontal. So theta dot is now non-zero. Theta equals 0. If you run it, you get lines like this. If b equals 0, right? And it turns out if you continue to plot things along, you'll get, wow. Yeah, that's right. I just drew my vectors too far. It looked kind of scary for a second there. Went a little crazy with the blue. Okay? In between, you get things like this, and things like this, things like this. Okay? And if you were to simulate that system, if you were to integrate those equations numerically, I said you couldn't do it in closed form, but you could certainly simulate them on a computer and track, if you were to start the system here, where does it go, then you'll find it follows these orbits like this, right? Which is, I started here, boom, 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 boom. If b equals 0, it'll just do this forever. Closed orbits, right? There's a particularly important orbit up here, which goes down and kisses this, goes over, kisses this one, goes back. What's that one? It's the one that starts right here. You just knock it just a little bit, it goes like this, right? I mean, technically, if it was exactly on this point, it would never move. It's a fixed point. But if I go just a little bit, or if I just knock it a little bit, then it'll go all the way around it. If it landed exactly on that point, it would stop at the other part. But if it was just a little bit off it, it'll go back around again, right? And then outside, well, there's also one over here. If I were to just take this whole thing and wrap it around 2 pi, I get the same thing again. So there's the same effect is going on over here. And you get this spooky eyeball looking thing, which is the eyeball of the pendulum. Okay? And then outside that, the curves go like this. And similarly down here. So we actually get a pretty good sense of what happens by looking at this thing in 2D, okay? This particular curve has a name. It's called the homoclinic orbit. We'll come back to that when we're doing homoclinic orbit. Yeah, some people call it, so homoclinic would be if it only touches one fixed point. So then you just get into a debate. Is this one fixed point or is this 2 different fixed points? So if you want to call them 2 distinct fixed points, then you'd call it a heteroclinic orbit. And I think people, for pendulums, since there's a wraparound effect, I've seen it called both. Okay, so where are the fixed points of this system? Can you do all the same beautiful analysis with in 2D? We said that there's a fixed point here. This is that unstable fixed point, right? The bottom is also a fixed point here. I got a 0 there. So is that fixed point stable? Show of hands. Who says it's stable? Who says it's not stable? The answer is, it depends what you mean by stable. Because this is where you start getting into more complicated things in nonlinear systems again. So it's tempting to say that's stable because, and by some definitions of stability, I would call that stable because if I start near the orbit, it stays near the orbit for all time. If I start near the fixed point, the orbits will stay near that fixed point for all time. It's not going to go off and go unstable. I wouldn't want to call it unstable, probably. But at the same time, it doesn't ever get to the fixed point. It doesn't get pulled into the fixed point. So then, maybe it's not stable. All right, so let's get a little bit more careful about stability. And that's the last batch of definitions I have to get across here. And then you've basically taken a semester-long course on nonlinear dynamics in a very shallow way in an hour and a half. So let me distinguish those two cases I said. One of them is it doesn't go away. What's that called? Anybody know the name for that type of stability? Oh, is it? Okay. In a linear system, I would call that marginally stable. But actually, I need even a different mechanism here. That's a good answer, but there's a more nonlinear answer to that question too. Lyapunov, right? So there's this notion of stable in the sense of Lyapunov. Lyapunov's an important guy. We'll talk about him later. Lyapunov, which is often short ISL in the sense of Lyapunov. And the idea there is that if I start near the fixed point, then I'll stay near the fixed point. So a fixed point x star is stable in the sense of Lyapunov. Now the way we're going to write that is a sort of a game here which says if you pick any ball around the fixed point, call it a Euclidean ball, that has radius epsilon, then I need to be able to pick a smaller ball that has radius delta, such that if I start the system inside delta, it'll never go outside epsilon. Let me write that down, and then I'll try to make sure it makes sense. Okay, so if for any epsilon, any small number epsilon greater than 0, okay, there exists a delta greater than 0, such that if my initial condition is inside the delta, if my x at time 0 minus the fixed point in some norm, you can call it the second, Euclidean norm if you like, okay, is less than delta. So this is a ball of points that are all less than delta away from the fixed point. Then for the rest of time, for all t greater than 0, x of t minus x star, so the distance between x and the fixed point stays less than epsilon. You pick an epsilon, I need to be able to pick a delta. Saying, okay, you want to stay within, 0.01 of the fixed point, then I'm going to start you 0.05 inside the, or 0.005 inside the fixed point, and I promise I'll never leave. And we'll understand that actually connects directly to Lyapunov functions, which we'll have a lecture on later. So the machinery maybe will make that more clear, why that seemingly obscure argument. That's different than being stable, asymptotically stable. Asymptotically stable means that if x at time 0 minus x star, if it starts close to the origin, then the limit as time goes to infinity, that thing has to go to 0. That means it's actually going to go to the fixed point. It doesn't say how fast it's going to go. It just says eventually, as time goes to infinity, the limit is 0. Okay? And then there are cases where you want to talk about how fast does it get to the fixed point. So you can talk about, for instance, exponential stability. Which would be, for instance, that x of t minus x star of t is less than some exponential. So if you want to talk about it gets closer at some exponential rate, then you can use the language of exponential stability. Okay, where the rate is alpha, right? Is that notation clear? Is that those ideas clear? Yeah.
You say the x star here is the same as the x star before, right?
I hope so. Anytime I'm calling a fixed point, and any fixed point, I'll put a x star. Yeah. There are multiple possible x stars. This is always, I should say, locally stable. Is locally. This is all a local analysis, so you do it in the vicinity of any fixed point. And I should have said that more carefully. This is actually not a full list. Nonlinear systems can do awesome, crazy things, right? They can converge in finite time to a fixed point. It's kind of a weird thing if you think about it. To have a smooth function that could arrive at a point in finite time. They can also blow up in finite time. That's roughly what I did in class, I guess. But no, but not formally. Yes, you can escape to infinity in less than infinite time, in finite time. That's cool, but don't make your robot do it. There's a whole bunch of cool things you can do with nonlinear systems. But these are all reasonable goals for us to design. And it matters, actually, when we're going to write algorithms. There'll be systems, for instance, where you can design an algorithm that will satisfy, like I will type in a different set of equations into my computer if I think I can satisfy asymptotic stability but not exponential stability. And there are systems that if you ask it to be exponentially stable, it'll fail. The algorithm will not converge. But if you ask it for asymptotic stability, it will, right? Walking is actually, or anything with friction is a good example of that. If I wanted to throw a box and have it land exactly at a point, for instance, if it landed right next to the point, nothing's going to sort of nudge it over, but it'll sit there forever. So if you ask it for it to be exponentially converging or even asymptotically converging, then you're going to fail. And it turns out that matters if you're picking up things with your hands. Like anytime you have contact or frictional contact, you end up having to go to stable in the sense of Lyapunov, and typically not asymptotic stability. Is that clear? Yeah? Feel free to ask if it's not. Okay, so now I want to try to give you a sense of what it means to be a control theorist. So I guess I didn't completely finish the story, I promise, but if I were to set b to be something greater than 0, then that's going to tilt these vectors in, and it'll end up with spirals that go in, and then you'd get asymptotic stability. But the the answer to this question now, you know, is that this fixed point is stable in the sense of Lyapunov. For the undamped system, that fixed point is stable ISL, but is not asymptotically stable, and then is certainly not exponentially stable.
So something is not asymptotically stable does not have a basis or basin of convergence?
So you can still talk about the region of attraction in the sense of a system that is stable only in the sense of Lyapunov. That's a reasonable thing to do. Okay, once I add damping back in, if I take B and drive it above 0, then my trajectories are going to converge in a spiral down to the fixed point, and I've regained asymptotic stability and, in fact, exponential stability in these cases. Okay? All right. In fact, let's think about what happens if you have U not equal to 0 in these equations. We know that there's 2 components to every one of these vectors I drew. The x component is just theta dot. So nothing I do with u, it's going to change. If I put u in, if I put torque in, it's going to change my acceleration, but it can't change the x component of this. But if I do apply a torque, I can change the direction of that vector. I can change it up and down. For any vector here, if I add u, I can move that vector up and down. And I can make u potentially be, if I can sense the system well and I can tell where I am on this plot, I could write a function u as a function of x that changes that picks that u for differently over the entire space. And I showed you an example, for instance, of just inverting gravity, which effectively erases all the horizontal components here, replaces them with the opposite one, and moves the fixed point to here. Right, that's something you can do with control. It wasn't what I advocate. Okay. So now this is the way to think about control, whether it's an autonomous car, a boat, a fish, or whatever. Nature, physics gave you some vector field. Maxon gave you a motor. Okay. Your job is to design those changes. Shift the vector field. Don't just erase it and draw your own vector field. That's bad, right? Shift the vector field a little bit here and there, okay? Change the arrows around, move the fixed points, control the system. That's the way I want you to think about control, okay? Optimal control is going to give us a language for doing that. But I think the right way to think about control and dynamics is that there's a flow out there in the world. It's a flow of information. It's a flow of mass. And you get to change it with control. And the game becomes, how do you write that function, right? To do the best possible control, make it robust to uncertainty, you name it. And that's what we'll try to do going forward. Okay, see you next time.